Right, so our primary topic here, closing out chapter 8, is going to be looking at kind of the most common acids and bases out there, and just talking about kind of what they are, what they look like, and just some general information and hazardous materials kind of concerns with it. So we actually started this discussion at the end of Monday's lecture when we did all of that work with sulfuric acid. We're going to pivot now to another very common strong acid, nitric acid. Where we see nitric acid most often is as an oxidizing agent and acid. So nitric acid has kind of dual roles as an oxidizer and as a corrosive, which makes it actually kind of doubly dangerous in that way. We find it in the use of manufacture for ammonium nitrates fertilizers. The nitrate on the nitric acid actually helps provide nitrogen for those fertilizers. Its oxidizing power is used in explosives. And we also find it as a very common component for nitrogen containing organic compounds, where we can use it to insert nitrogen into a carbon chain, which has some particular effects and uses in manufacturing. Now, on its own, pure nitric acid is colorless. If you get it straight from the manufacturer, it's going to be kind of a slightly viscous, certainly thicker than water kind of consistency, but crystal clear. What happens over time, though, is that nitrogen dioxide will happen as the nitric acid starts to oxidize stuff. And nitrogen dioxide being kind of a brownish orange gas, as it is released and it gets trapped in the nitric acid, that nitric acid can take on kind of a yellowish tint. And the longer it sits, and the more it's exposed, especially to open atmosphere, the darker that color can get. Now, just as a comparison, we look at nitric acid on the left-hand side versus sulfuric acid on the right-hand side. And we can see that with limited exceptions, they're very similar in a lot of ways. Neither is flammable. Both pose considerable health issues. And although nitric acid on its own is an oxidizer, it carries no stability risk necessarily to it. It itself is not explosive or unstable in any kind of way. But we can see that sulfuric acid does have a moderate issue where we have trouble where it could not come in contact with water in certain circumstances. It has an unstable kind of nature that could potentially lead to explosive or unstable behaviors if we shock it or heat it up real strongly. But in terms of the placards that we see corrosive placard for both of them. For the nitric acid, we also see this flaming circle, the oxidizer placard. Nitric acid, because of its oxidizing power, does have some reactivity concerns that we don't see with other acids. So, for example, we talked about the reactions of acids with metals a couple of days ago. And we mentioned specifically that there were some metals that were completely inert toward acid. things like copper and silver, gold, platinum, palladium. Well, some of those metals, copper in particular, run into problems with nitrates. Nitric acid is actually strong enough to oxidize them. They will dissolve in nitric acid. When they do, we usually get a combination of nitrogen-containing products as a result. Those can range from nitrogen gas, which is relatively harmless, nitrogen monoxide gas, which is not great to be around, nitrogen dioxide, which is downright poisonous, and some other substances as well. So nitric acid has an ability to chemically attack because of its oxidizing power. And that's one of the reasons why we have to be really careful with it as opposed to some other acids. And again, when we see nitric acid coming into contact with metals, our primary products are nitrogen monoxide and nitrogen dioxide. Of the two, nitrogen dioxide is the more dangerous one. It also generates for us kind of a rust-colored gas that can range anywhere from like reddish orange to kind of a brownish color. Usually pretty easy to spot when it comes. Nitrogen dioxide also one of the gases responsible for smog, which is why you see that hazy kind of consistency in smog. That's usually the nitrogen dioxide mixing with the water vapor in the ground level fog to create kind of that brown haze. And the reason smog is dangerous is because that combination of ingredients can lead to nitric acid, nitrous acid, some other acidic materials as well, which is not terribly great if you breathe it in. Nitric acid can also oxidize nonmetals. So, for example, you can corrode carbon and sulfur using nitric acid, especially hot nitric acid. You can also see reactions between nitric acid and various volatile organic chemicals, especially those that are flammable. Of particular interest are things like solvents, turpentine, acetone, ethanol, commercial agents like acetic acid or nitrobenzene, aniline. These substances will ignite, burst into flame when they come into contact with hot nitric acid. Nitric acid oxidizes them, and their byproducts will ignite into basically a fireball of sorts. The one thing that we notice with nitric acid more than others is its reactivity. It has a wide range of reactivity because of its corrosive nature and because of its oxidizing power. So naturally, we expect that as far as like what we would expect on the human side of things, reactions there are pretty nasty at times as well. So when you're exposed to nitric acid, the primary thing that happens, even at low levels of exposure, is that it is going to corrode your body tissues. And it's going to do so in not the same way that other acids do. Yes, it's going to cause burns. It could cause, nasty skin disfigurement in certain circumstances. But even just with small level exposures to the vapors on concentrated nitric acid, you can get this yellow skin business. So with nitric acid, well, one risk that you always run in working with it is exposure, is yellow skin. It can happen in very low concentrations. It can happen in very short duration periods of time. Not so much with low concentrations, but low exposures. You have a bottle of nitric acid that's concentrated, open it up, you put your hand over the mouth of the bottle, and if any of that vaporizes and comes up in contact with you, you can get a little yellow mark on you from that. The wounds that, such as they are, heal very slowly, even for just a little bit of yellow skin, where you don't feel any effects. It doesn't burn, it doesn't tingle, it doesn't itch, but you've got a yellow mark on your fingers. Because of what it is reacting with, it's reacting with the proteins in your skin. Those don't just repair themselves overnight. It takes days, weeks even sometimes, or even the smallest exposures to get rid of that yellow skin mark. Now, the actual product there is something called xanthoprotic acid. You don't need to know that, but that is what is taking place. That's what happens between the nitric acid and the proteins in your skin, and that's what causes that yellow mark. So that's all for nitric acid. Let's take a look at another common acid, hydrochloric acid. Hydrochloric acid can also be known by a common name, muriatic acid. Muriatic acid can be used for maintaining proper acidity and pH in pools. Where we see it most often is actually in toilet bowl cleaners and other household cleaning products. Now, if your toilet product uses bleach in some kind of way, it's not going to use hydrochloric acid. Its cleaning agent is bleach. But it is a very common snow bowl. It's probably one of the more common trademark names for hydrochloric acid based cleaners. If you use Clorox, Clorox is a bleach. So the bleaching agent is what is going to clean and disinfect the toilet instead of hydrochloric acid. But there are certain cleaners that do use hydrochloric. We also see hydrochloric used as a processing agent for food. We can see it used in activating petroleum wells and in just general chemical production. So again, this is a very common acid. And if you think about some of the labs that you've done this semester, hydrochloric acid has been a part of a good number of them. Anything that we use with acids and bases, usually the acid of choice is hydrochloric because it doesn't have the oxidizing power of nitric, doesn't have the dehydrating power of sulfuric. It's a little bit more stable, a little bit less reactive, even though it is still a strong acid. Primarily, we see it in educational facilities and research facilities such as this one. Usually we store it in plastic containers. Those plastic containers are corrosion resistant and last a long time. They're made out of the same kind of material that permanent water bottles are made out of, Nalgene. On its own, hydrochloric acid is colorless, but it does fume, meaning that on heating and even just at room temperature, If you were to stick your nose right up to a bottle of hydrochloric acid, you would smell something, and that smell would be pungent, and it would make your nose tingle because it reacts. How we get hydrochloric acid is we take the gas hydrogen chloride and we dissolve it in water. And that's one of the reasons why it's also a fuming kind of agent as well, because its solubility in the water does have a limitation. And over time and through use, that hydrochloric acid can make its way out of the water. Another example of an acid that is in somewhat common use is perchloric acid. Perchloric acid is HClO4. Like the other three acids before it, it is classified as a strong acid. Its primary use is in the chemical industry. It is also used as an electroplating agent. So you do find its use in some things like auto body shops for chroming purposes. We also find it in things like the fireworks industry. It does have oxidizing power. That perchlorate ion is an oxidizing agent, but it does not oxidize with nearly the same ferociousness, I would say, as nitric does. It's not nearly as commonly used as nitric acid. Now, as a strong acid, it will act as a strong acid, strong reacting agent, both in hot temperatures and in cold. The more concentrated it is, the more powerful it is as an oxidizer. But it loses its oxidizing power relatively quickly the more dilute and diffuse it gets. The main reason we are going to talk about perchloric acid is this right here. In its hot concentrated form, it can react with organic compounds like an oxidizing agent. So again, very similar to nitric, but with one important difference. There is a greater explosion hazard for the combination of organic materials and perchloric acid. They have to be kept separate from each other. So that oxidizing power and that explosive potential is great in something like a firework. Because in the end, you want a firework to explode. That's the whole purpose. That's the whole point. But if we're just holding them here on the ground, we want to make sure that we keep them apart from each other, because their mere presence with each other is enough to start a fire, is enough to create a potential explosion situation. So while it is not nearly as common in use as nitric acid, and in a lot of ways isn't nearly as powerful as nitric acid is, because we need it to be in a high concentration to really work. Perchloric acid does have some pretty considerable hazards associated with it. All right, let's look at hydrofluoric acid. Hydrofluoric acid is HF. On its own, it is a colorless acid. Can exist as either a fuming liquid or in the vapor state. Where we see it primarily in its use, hydrofluoric acid can be used as in the glass industry as a treating agent, either to polish glass, to etch into the glass, or to create that frosting effect in glass. For certain things like decorative glassware or like shower glass showers that have the kind of frosted appearance. Hydrofluoric acid is unique in the sense that it does not, because of its reactivity with glass, all those effects that we just talked about are direct results of the reaction between hydrogen fluoride and the silicon dioxide in glass. And so because of that, we can't store hydrofluoric acid in glass. We have to use specialized plastic containers to store it because it reacts with everything else. So you may have noticed that some of our containers up in the laboratory for acids and bases are made out of thick walled glass. Not the case for hydrofluoric. In fact, hydrofluoric acid is not something we keep around very much because of some of these other reactions that it can do. So other uses besides glass, we know that it can be used to pickle brass, copper, and some alloys. So we use it as a refining agent. We can use it to produce computer chips. So help to purify silicon. And we can use it as a catalyst, where it can be used as a way to speed up certain types of chemical reactions by creating fluorinated products that are more reactive and therefore go faster. Main concerns with hydrofluoric acid, well, obviously as an acid, we have to worry about skin burns, both at the surface level and at deep levels. The other big thing here is hypocalcemia. If hydrogen fluoride penetrates deep enough into you, it can start to react with the calcium in your bones. It can start reacting with the calcium in your bloodstream. And here's the real dangerous part of that. Calcium fluoride, the product that results from that chemical reaction, doesn't dissolve in water, doesn't dissolve in your blood. And so you literally start getting rock forming in your bloodstream. As you can imagine, that usually doesn't spell good things for your health. Get high enough exposure, you can be dead within a matter of hours. Hydrofluoric acid can also interfere with your nerve function. And probably the scariest sign of all of them is that because of the nature of the stuff, you may not even realize that you've been exposed to it until hours later. So there might be a spill or something like that happens. They get everybody out of there, and people don't actually start to notice any effects of it until considerably later. All right, we've got a couple more acids to work through here before we get into some common bases. Phosphoric acid, H3PO4. This is the only acid that we know of that contains phosphorus. Its use is varied. It is found in some cleaning products. It can be used in certain corrosive and abrasives to take off residues like rust or hard water. Where we see it probably the most often is in soft drinks. Colas in particular will use phosphoric acid as a stabilizing agent, as kind of something to help maintain the flavor and the gaseousness of the soda. Food products also can contain it. We also find it in the use of making phosphates and fertilizers. A lot of the phosphorus that comes in commercial fertilizers comes from phosphoric acid. We also find it in certain kinds of pesticides and as a priming agent for steel when you go to paint. So we rub the phosphoric acid on the steel. Phosphoric acid helps to treat the surface, allows the paint to stick to it more easily, so that it doesn't chip off quite as easily. It doesn't rub off nearly as quickly. We can also talk here about acetic acid. Acetic acid is probably our most commonly encountered organic acid. Its chemical formula, CH3COOH, sometimes shown as C2H3O2. It's an organic molecule. So it is made out of a carbon chain, has an acid group on it. Where we see it used, acetic acid is often used for quite a few different kinds of chemical products. In particular, the creation of a number of different kinds of esters. So products like ethyl acetate, vinyl acetate, cellulosic acetate. A lot of these are precursor products for other larger organic materials, but they kind of get their start. A lot of times when you make synthetic chemicals, it comes in stages. Make a pharmaceutical product that maybe has 50 carbons in it. You kind of build it up in steps. I start with this, I add a little bit to this to get this group on it, I add a little bit more over here to get this group on it, and it kind of comes out in stages. A lot of those stages to set up the larger molecule come from reactions of acetic acid with other small molecules. As far as its oxidizing power goes, it doesn't have any. And as far as its acidity is concerned, it's pretty weak. But what we know most about it is its smell. Acetic acid has the smell of vinegar, because vinegar is a commercial product of acetic acid and is about a 5% solution. So 5 grams of acetic acid for every 100 grams of the solution. One other thing about it is that it is flammable, or at least combustible. In its concentrated form, acetic acid is a category 3 flammable liquid according to OSHA. According to NFPA, it's a class 2 combustible. So we know from our definitions of those terms from a couple of units ago, that means that it is something that is, doesn't have a super high flash, low flash point, but get it in the right circumstances at a hot enough temperature, it will ignite. And this is where we get into that, what classifies as ignitable, what classifies as concentrated. We have to have an 80% or higher concentration. So the vinegar that you buy to make salad dressing or to use as a cooking product, that isn't nearly high enough concentration to actually get it to burn. That's only 5%. To be flammable, it has to be at least 80%. And again, remembering our definitions of combustible liquids, we know that it also has to be at a high enough temperature. Flash point for these is somewhere over 100 degrees. So it's not even going to be combustible at room temperature. We're going to have to raise its temperature. It's going to have to be hot to get it to ignite. So that's our acids. Let's look at some common bases. So we'll start with sodium hydroxide, perhaps the most common of the common bases. Sodium hydroxide, NaOH, otherwise known as lye or caustic soda, is found in a number of different kinds of applications. We find it used in a number of different kinds of cleaning agents. We can also find it in the use of purification for petroleum products, or creating recycled rubber products, processing textiles and fabrics, paper. As a raw material, we can see it used in the soap making industry. We've already talked a good bit about saponification reactions. We can also see it used in a number of different chemical materials, things like rayon, which is a type of manufactured fabric, cellophane, plastic wraps, and other kinds of chemical substances. Sodium hydroxide is very, very, very common in its use. So the textile industry would basically cover any kind of material good that is either fabric or kind of like a manufactured substance. So things like linoleum, flooring, or fabrics that make up shirts or pants. Even some kinds of fabrics like the polymer materials that make up carpeting or mattress pads or other things. So it's kind of a wide industry, but it's that kind of material. All right, let's move on to potassium hydroxide. Potassium hydroxide, otherwise known as potash or potash lye. Chemical formula is KOH. Where we see potash used is in two different areas, well, maybe three. We see it used in fertilizers. Part of the reason there that can provide some of the necessary potassium that goes into the ground. We can see it in the soap making industry. The difference between it and sodium hydroxide tends to form soaps that are kind of solid and cake-like. So think of your bar soaps when you think of sodium hydroxide. Potash creates a softer soap. This is more like your liquid soaps. It can also be used in the pharmaceutical industry. Potash used to be used in liquid drain cleaners, We see that more now with sodium hydroxide, though. So if you buy a bottle of liquid plumber to open up your drain because it's moving up slowly, what you'll find in the ingredients there is usually a combination of bleach, which is what gives it kind of its smell, and sodium hydroxide, which is the chemical agent that is going to be used to react with whatever it is that is gunking up your sink, usually hair products and other kinds of stuff, and get it to open up the sink or open up the drain. Calcium hydroxide, chemical formula CaOH2. This is also known as slake lime or quicklime. We see this used in a number of different applications. Probably the most common is as a building material. This is used in the production of common materials of mortar, plaster, and cement. We also see calcium hydroxide used as a neutralizing agent for acids. All right, so the last thing that we want to talk about here to kind of close up this unit is just some general workplace regulations about corrosives. Now, OSHA is overseeing all of this. And basically, the OSHA mandate says two things. Employers have to post that there are corrosive materials present in the workplace, and they have to put on accident prevention tags and warning labels on the containers themselves. So they have to designate the area and the container. That's what OSHA says that they have to do. Designate the area and designate the container. The signs that they can use can be very general. Something as simple as just the placard itself. Or they can be just caution signs, such as these. The other thing that OSHA requires is that they need to provide some kind of suitable means of protection and suitable means of treatment in the event of exposure. And what do those look like? Well, you've seen them in the lab. Eye wash stations, safety showers. So in the event that one of those caustic materials gets into your eyes, you can go over to the eye wash station and flush them out. In the event that you get a large amount of acid all over your body, you can run to the safety shower to scrub that material off of your body before it starts to eat away at you. And again, you've seen in our laboratory, we have safety shower setups exactly like this. Eye wash on the bottom, shower on the top. And there are usually some kind of sign in and around the area to designate that they are there. So that's all for chapter 8. So when we come back on Friday, we will pick up and start looking into chapter 9. Any questions before we go? All right. Have a great day. I'll see you Friday.